Today we will start a series of lectures or videos in particle physics. So let's write here particle physics. But first, in this first video, I would like to introduce or to remind Klein-Gordon equation. So first it's Klein-Gordon equation, and then second we have Dirac equation. So first of all, why do we need Klein-Gordon equation when we can introduce things or explain things in quantum mechanics with Dirac equation? Klein-Gordon equation, it is very important because first of all it was the first attempt to relativistic quantum mechanics, but also in quantum field theory it explains multi-particles or systems that have many particles with spin 0. So we still need the Klein-Gordon equation. But even before that, so let's write here like a 0, we had Schrodinger's equation, which was something like partial of psi partial of t and minus 1 over 2m partial of psi squared partial of x squared plus some potential. The problem with this equation is that it is not relativistic, and it is not Lorentz invariant, because here we have the first order in time, so the derivative of first order in time, but here we have the second derivative, so it cannot be Lorentz invariant. So the equation for quantum mechanics should satisfy this equation for energy momentum relation, so p squared plus m squared. So the energy is p squared plus m squared, which is Einstein's equation of energy and momentum. So now suppose we have this equation and then we apply this to the psi of x. So psi of x, it's a wave, represent a wave function here. Now, but we also have to remind ourselves that energy here it's represented by this operator, so partial derivative in time, and the momentum it's represented by partial derivative in x, which when we have more than one dimension, like 3 dimensions or 4, we can write as del operator. So now let's continue to apply this energy equation to this function here, and then we can find that E squared we have times psi equals to p times psi plus m squared psi. And then we have here I squared, so we replace this here and this equation for p, partial squared psi partial of t squared, and here we also have minus 1 squared is 1, so we have I squared partial squared partial of t squared plus m squared psi. And now we can arrange this equation somehow, so we can eliminate I squared, and then we have partial squared of psi partial of t squared, which is partial of psi partial of t squared. Oh, sorry, this should be So this here should be partial of x squared. So here we have partial squared of psi partial x squared minus m squared psi. Now we can bring this part to the left side, and we can have an equation like like this form: psi minus m squared psi. Okay, so this is basically a Klein-Gordon equation, but we usually write in the better form, for example, like in covariant description. So the index mu, and here is the index mu, is partial of t squared, t minus partial squared partial of x squared. And then in any case, if we have, for example, more than one spatial coordinate, we can add partial squared partial of y squared minus partial squared partial of z squared. But in this case, we are working with one-dimensional spatial. Now, if you replace this equation, this form in the Klein-Gordon equation, then you get partial of mu minus plus m squared psi equals to 0. So this is the Klein-Gordon equation, which is Lorentz invariant. So this is very, very important. But as we'll see, it is not the whole story, because now we will try to calculate the probability density and probability current. So when you calculate probability density, you find that it is proportional to the energy, and the energy here has the negative values. So something it's not right. But we can start with the equation. So we have partial of psi partial of t squared, which is equal to del squared psi minus m squared psi. And this, in this equation, you act from the left with a complex conjugate. So you can act from the left, and then you get something like psi star partial squared psi partial of t squared psi star del squared psi minus m squared psi star psi. So this is the first equation. Now we have to complex conjugate the whole Klein-Gordon equation. So in this case would be partial squared psi star partial of t squared del squared psi star minus m squared psi star, and then in this case we add to the right with the psi, and then you get something like the first term times psi del squared psi star psi minus m squared psi star psi. So this is the second equation. Now what we do is we subtract the first equation and the second equation. So basically 1 minus 2. So the left side with the left side and the right side with the right one. So at the end, I think it is very quite simple. Just to subtract the parts, we get a form that is psi star partial squared psi partial squared psi partial t squared minus psi partial squared psi star partial t squared, which is equal to the psi star del squared psi minus m psi minus psi del squared psi star minus m squared psi star. And now you can arrange the equation in a form like, for example, partial of t. You have psi star partial of psi partial of t minus psi partial of psi star partial of t, which is equal to del psi star del psi minus psi del psi star. Now you have a continuity equation from fluid mechanics or from electromagnetic theory. So you can write plus so here in this equation the J is the current and the rho is the probability density. So here is the probability density. So now when you compare these two equations, you find so here you have del, here you have del, and here you have partial of t, here you have partial of t, and here you have the probability density. So the probability density rho, it is psi star partial of psi partial of t minus psi partial of psi star partial of t. So you have here a form of the probability density, but as you know, the energy operator in quantum mechanics is this one. So what this means is that probability density is in the right, let's say, sorry, it is proportional to the energy. So from here you can see it is proportional to the energy, but we know that relativistic energy is given by this equation, and then from here you have also the negative part of the energy. So this might be p squared plus m squared. So what in this form the probability density should be real, and it's saying that you have something that is proportional with negative thing, which is not possible in the physical quantities, because we don't measure the negative things. So what is the solution to this problem? The solution came from Dirac, where he tried to solve the problem, and he started with an equation that is proportional in time and proportional in space, so the first derivative. But he also added alpha, and he added a beta here. So basically you need to find what is alpha and what is beta. So from this form you can see that it might be some kind of vector or some kind of matrix, and then also this one maybe should be a matrix, maybe should be a number. So he started from this equation, and then so if you write this in a longer form, it's I partial of t psi, and then it should be minus I alpha of x partial of x minus I alpha of y partial of y minus I alpha z partial of z plus beta m psi. So we need to find what is the alpha x, alpha y, and alpha z. So we can, let's say we can square the equation, which is minus partial squared of psi partial of t squared, and then here you have alpha of alpha x partial of x plus alpha y. So here you have an I, here you have an I, partial of y plus I alpha z partial of z. So sorry, here you have minus, no, it's okay. So here you have a plus. Sorry for the confusion. Here should be plus beta, here should be minus beta m, and then you have the same thing again, psi. So you can multiply both equations. So you can find partial squared psi partial t squared, and then you need to find so you have alpha x squared partial squared psi partial of x squared plus alpha y squared partial of y partial of psi partial of y squared plus alpha z squared partial squared of psi partial z squared minus beta squared m squared psi. Then you have also additional terms, so cross terms. Let's say alpha x alpha y plus alpha y alpha x partial squared of psi partial of x partial of y. Then you have alpha x alpha z plus alpha z alpha x, and then you have the same form here. And then you have alpha y alpha z plus alpha z alpha y with the same form, plus you have some terms like I alpha x b plus b alpha x partial of psi partial of x plus I alpha y b plus b alpha y partial of psi partial of y. So here you can see the full form, but this equation this equation should satisfy the first of all the Klein-Gordon equation and the energy momentum relation E squared, which is equal to P squared plus M squared. So in order to satisfy the Klein-Gordon equation, these terms must vanish. So for example, these terms should add to 0, this add to 0, this add to 0. So from this we can find what are the properties of these alpha x, y, and z. So the first thing is that alpha j, alpha k plus alpha k, alpha j should be equal to 0. But also alpha j beta plus beta alpha j should be equal to 0. And also alpha I squared should be equal to beta squared, should be equal to identity, where I is x, y, and z. So this is these are commutational relations. So or we can say better that this is the commutation relation. So we know certainly that numbers do not have these kind of properties, but we know that the matrices have commutation relations. So in order to find these commutation relations, we also need to show that these alpha j, so we call now matrices, they should have the trace equal to 0. So trace of alpha I should be equal to 0, because let's say you have the alpha I, which you apply in a state x, and then you find some eigenvalue lambda. Now if you multiply this in both sides, or if you act with an alpha I, let's say from the left you find alpha I squared x, then you have lambda alpha I x, so this is 1, and from this you can conclude that x is lambda squared x. So you have lambda plus minus 1. So the eigenvalues are plus minus 1, but we know that the trace is the sum of so the trace is the sum of eigenvalues. So here we have 1 minus 1, which is equal to 0. So the trace of these matrices should be also equal to 0. Now we know only one kind of matrices, let's say, that obey these properties, and these are Pauli matrices. So we can build, later gamma, these alpha i's, we rename them as gamma, which we could now call Dirac gamma matrices. So we can find these Dirac gamma matrices in terms of these Pauli matrices, where we have so the Pauli matrices are Cx 0, 1, 1, 0, Cy, which is 0, minus 1, or I think it's minus I 0, and Cz 1, 0, 0, minus 1. So alpha i's are four-dimensional matrix. So one thing also, alpha i's should be in odd dimension, so it cannot be in even dimension. Alpha i's are 4-dimensional, so the smallest dimension after 2 is 4, which is odd dimension. So we can build these alpha i's in terms of these sigma x, y, and z, and the general form of these are alpha I are 0, psi 0. So when you insert psi x here, you have the 4x4 matrix. Then also the beta matrix, it is the identity matrix. Beta is like this, but I represent the identity matrix. 1 0 0 minus 1, so the diagonal is 1. So here we have showed the so why the Dirac equation solves the problem. Now the question is, what does the Dirac equation does better than Klein-Gordon equation? Well, when you try to calculate the density, you find that the density, you go the same process. So you conjugate the Dirac equation, then you multiply by psi, and then you also multiply the equation by psi star, and then you find that the density is now real. So it is psi daga psi, which is psi1 squared plus psi2 squared plus psi3 squared plus psi4 squared. So why psi1, psi2, psi3, and psi4? Because psi, it's a 4 spinner. psi1, psi2, psi3, psi4. So it's a 4 spinner. And the psi daga would be psi1 star, or daga transpose, psi2 daga, psi3 daga, and psi4 daga. So here you see that the density it's real, but in the other equation the density was proportional to the energy, which for negative energy we cannot solve it. So but for this video, I think this is all. Later we'll explain what are the physical consequences of the Dirac equation, because this is just the mathematical thing, but also Dirac equation. So these 4 degrees of freedom, they can explain the particle, free particle moving in a field. They can also explain the spin of the particle, the angular momentum, but these things we will discuss later. So thank you very much for watching, and we see in the next video.